Thank you very much, and brilliant overview about beam shaping, because my project has a little bit about beam shaping too. In fact, is there any laser application that doesn't have beam shaping in it? Well, this particular project I'm working on is called Soni Shape Laser. Soni Shape Laser is funded by Innovate. We are going to crack 6082 welding for good. I want to tell you a little bit more about why we want to weld aluminium. Flippin' heck. It's so tough. It really is really tough. And of course, it doesn't like being welded. Can I pass this round? 6082 aluminium. 6000 grade aluminium is pretty much all the same. They don't like being welded, but they're so tough. They're as tough as steel, they don't rust, and they're a third of the density. It's a no-brainer why we want to weld them. Okay, so everybody wants to use them. We've got a project where Soni Shape Laser, clue is in the title. Soni means sonification, well, for me it means ultrasound. A shape means beam shaping. And the lasers, obviously, we're laser welding this beam. This plate of material I'm sending around the room, it's sharp, so don't cut yourself on it. But it shows you a few of the things that are typical on an aluminium weld. So what we're trying to do, we're trying to weld battery cases. So it's an application, specific battery cases. So we're going to take from what Gwen's just said, we're going to narrow it right down just to one application. We want to use 6000 grade aluminium for making a crash barrier, a safe box to put your batteries in. That's what we want. So if the worst happens and you hit the wall and your car's written off, so we want this battery case to look after the battery and look after you and make sure the battery doesn't catch fire, whatever. So Soni Shape Laser, the whole idea is we take the process and we make it better. And of course, we're going to use beam shaping. We're going to use ultrasound. I'm going to tell you a little bit more about that in a minute. But we've got a brilliant team. This project, I've got a brilliant team. I've got Laura down here, but the main man is away today. He's hiding in Sweden somewhere. Warwick University, WMG have been amazing. They are the welding gurus of the Midlands, not far from here, of course. So we've got a dream team, really. We've got Power Photonic on the beam shaping side. Thank you. We've got Emma in the crowd here. Thank you. And Ionetic, also no one from there today, but they do the battery packs. This is us. This is us at the kickoff meeting. So we're going to make a demonstrator over 2 years. We're going to make a demonstrator battery case out of 6000 grade using these tricks, but we're not going to use a filler wire. We want to be able to weld a case straight just by pointing a laser at it. So let me talk about the first one, Power Photonic. Power Photonics, based in Scotland. They make the optic that we are going to use in the laser. They make the optic by cutting a piece of glass, and you make the piece. The optic is then going to change the shape of the beam. Now, Emma tells me that we sort of rough cut it, then you smooth it off, and actually, there's almost any shape you can make, as Gwen told us, there's almost any shape you can make. But we make it, this particular project, we're going to rely on a single piece of fused glass and put into the optics in a Precitech head, and then we're going to get the beam shape. But what beam shape? I think that's the confusing bit for me. Everyone talks about shapes and beams and stuff, and I go, what do we need? So let me just say, Power Photonic, we can make almost any shape, but this is very typical of what we're going to look at. We've been looking at this corn ring. The ring is a ring around the outside. The core is the central part that does the main welding. But the bit that does the processing of the material, the preheating and the post-heating, the bit of where it's spreading out the heat to try and reduce the stress, that's what we really want. We don't want 6082 as I can't think of a polite way of saying it, but it's a bugger for cracking. And if it cracks, it gets hot cracking, it's terribly easy to, well, it just fails. But also welded 6082, when you make a weld with it, it goes soft. And that's what we don't want. Anyway, the beam shape, we're going to go with a beam, we're going to go with a core and ring, and it's got a nice waist to it. So it's got quite a bit of flexibility to being in and out of focus. When we're talking about a specific application, we know that box section aluminium isn't necessary, it's pretty straight, but when you cut it and start making a fabrication out of it, there's a good chance you'll be out of focus at some stage. But that picture on the far right-hand side shows to me that you can be out of focus, but you still get the good treatment. So this is typical where you put the beam shape. So the optic that I showed you on the first slide would go in the optic somewhere in the collimator. So the collimator, so there's two places you can put it there, and we recommend you make it somewhere easy. But it's got to be completely sealed in so it doesn't get dirty. So, Paraphotonic do the beam shapes. Then what we've been doing, we've been then asking our colleagues at Warwick, at WMG, if they would do a simulation. And they're all those beam shapes there, 1, 2, 3, 6, 7, 8, 9, 15 of them, all come up with different ideas, different techniques and tricks for welding aluminium. We've come up with just 4 out of those, and we're coming up with around about an even amount of power in the ring and in the core. And we do that by looking at the using a thermomechanical model, which I've been told all about from WMG. The thermomechanical model looks at not just the way the material heats up and the way the heat is distributed, but also looks at the latent heat from when it goes from a solid to a liquid. And the liquid to solid go back to solidification. And this is really crucial when it gets to this particular material, the 6082. Let me just show you a little bit about what they've been doing at WMG. So, here you've got very simple geometry. It's a bit like the plate I've sent around the room. Very simple. We put a single beam down the middle. We join 2 bits of material together. And you can either have a single spot in the middle like we did in the old days, but now we've got a spot with a ring. And to simulate that, they've been using a process called COMSOL. Now, COMSOL looks at the geometry and the heat input and the speed and all the different variety of the parameters that you put in. Now, on this, I don't know, can I point at this? I can't point at that. This validation here, this is the simulation. This is the actual. So this is a macro of the joint cross-section of the actual weld where we cut it up and we've looked at it and we've said that's what it should be, and that is what it actually is. So it's very close. The validation basically says the simulation works. And the pretty video on the other side, we've basically got displacement showing the plate heating up and cooling down as we're going along. But it's also all about, let me show you. This is a weld pool. This weld pool here, this is the point where you think the spot of the laser is, but it's going this way. So you have the weld pool behind it. The blue part of that weld pool is the mushy zone, if you want to call it. It's a bit like when snow and ice, you've got something that's not quite ice, it's not quite snow, but it's nearly going to solidify back into solid metal. I like the idea of the mushy zone. We've basically got the opportunity to try and reduce the stress before it all shrinks back and solidifies back into a solid. This is what we're trying to do here. And this stress line here, we're trying to minimize the stress that we're putting back into the solid material. That is crucial to stopping hot cracking. Anyway, so we've run four specific power variations between how much power's in the ring, how big is the core, how big is the ring. There's 4 different combinations, and we're now going at this stage of the project. We're sending that off back to Power Photonics to make those beam shapes. So we've simulated those welds, and so at the moment we're waiting for the beam shapes to be made, and then we're going to do some further work to see where the welds are. Now, let me tell you about the Soni bit about the welding. So this is where cars come into it. Soni is all about ultrasound. This is an ultrasound transducer. This is about 28 kilohertz, this one. The 20 kilohertz is even bigger. But what we've been doing, we mount the transducer on the plate. The plate that's going around the room would be in the middle there, and we're welding the middle. And the transducers are mounted on the outside and clamped down under these clamps. The transducer vibrates the plate. It really vibrates. You can feel it buzzing. You know, you really can feel it, so that when we get the weld, we've already, at this particular point, we haven't got a beam shape on this. We're just using a standard laser with a sconic head, and we're doing some standard welds, and we're doing some baseline work. What we do with that plate that I'm going around the room is we then weld it, then we cut it into lots of strips, like we did on the far side there, and then we pull those strips to see how strong the weld is. The results of that is that without any ultrasound and without any other factors, what we call the baseline, we get a fairly good result, but it's fairly low. It varies quite a lot. This bar here, this bar shows you the standard deviation. So some are good, some are bad. And so these are the ultrasound results. And of course, what we're trying to do with this project is try not to use filler wire. Unfortunately, filler wire does give us a really good result. But we're trying not to use filler wire, so we've got that in there as an idea of what we've got to try and match. So ultrasound is giving us a good result, but not enough to push us over the line. So let me tell you, what we looked at the welds, we've been trying to work out how we simulate the weld, which has got ultrasonic vibrations going on in there. And it's hard to say exactly what's going on, but it's clearly there's something going on which is changing the structure of the weld. In this case, maybe the grain refinement. This shows you the grains that are in the weld after we've solidified. We cut up the weld after we welded it, and we then do a macro of that, and then we can do this EBSD analysis. It shows you the shape of the grains, and there's no doubt the ultrasound changed the shape of the grains. And we want to change everything from columnar grains to this equiax grains, which is the smaller refined grains. And the ultrasound excited weld definitely has more of these equiaxed grains, and we have a grain refinement, which is good for the weld, which is stronger. So this is research, and we are not at the final part of it yet. So work in progress, good work in progress, and so we're getting there. Quick thing about Ionetic. Ionetic are a company down in Brackley. They make battery cases. That is a battery case. It's a huge thing. It's a box, basically. Sits in the bottom of a car, and it has all the cells in it. And it's really important that those cells are looked after. It mustn't be able to pierce it, you mustn't be able to bash it, it mustn't be able to get anything in it, it must be totally water-free, it must be sealed IP69. That is the challenge. So, next time I come to this in 27, hopefully we will be talking about the end result. So we're going to make a demonstrator battery case with all the various different joints in it, with a Soni shaped laser, but not quite yet. We're going to get there. This is my team. Thank you so much for listening.
Thank you very much, Phil. Very interesting talk. There is time for one or two questions.
Thank you. Fascinating presentation. Were you measuring the temperature of the base material before you were doing ultrasonic? Are you thinking maybe the ultrasonic is perhaps preheating the material for you, or are you looking at the ultrasonic specifically in the weld pool agitation?
We didn't know any change of temperature with the ultrasound. The ultrasound it's fizzing away, buzzing away, but it's not really changing any temperature. So we're not looking for a change of temperature, are we, Sam? No, but it's an interesting thought, though. And basically, the ultrasound really just changing that grain refinement is all we want. If we get it all nice little grains.
Cool oscillation then almost really is what you're achieving by doing that?
Yeah, we're getting some of that, but we want to optimize that.
Right.
So at the moment, what we're doing, we're just doing weld trials. We're seeing what makes best, and then we're going down that road. What we want to try and do is get one of the bright guys from WMG simulating it to find if we can find a reduce the amount of weld trials we do to actually get to a software solutions that would say, why don't we try that? So that's watch your space. Thank you.
Thank you, Phil.